Hello everyone, my name is Jiajun Xin. Today I'm going to present our work, Check Before You Solve Verifiable Time Block Puzzles. This is joint work with my advisor, Dimitris Papadopoulos. First of all, let's recap what are time block puzzles. Time block puzzles allow a puzzle generator to produce a puzzle that can only be solved after T sequential computational steps. And time block puzzles already found numerous applications. The first one is timed transaction for blockchains to resist front-running attacks. We will discuss this example in more detail shortly. The second one is payment channel networks. For example, hashed time lock contract is based on the time lock technique. The third one is sealed bid auctions, which is the most classical application of time block puzzles. The core of time block puzzle is asymmetricity, which means puzzle generation is easy, but solving takes T sequential steps. This property is essential for time block puzzles and very important for its application scenarios. However, we observe that this property can be a limitation condition for some cases. An attacker can utilize this property for attacks. For example, an attacker could generate a random puzzle and falsely claim it contains, for example, a valid transaction, and thereby wasting others' computational resources. In conclusion, solving takes time, but trust cannot wait. Solvers must confirm every delay is meaningful and every effort is not wasted before devoting their efforts. And let's take a real-world example to see why this is the case. Let's take the example of timed transactions to resist front-running in blockchains. In this setting, users submit their transactions publicly to the mempool. And a validator is going to examine the transactions and confirm the transaction execution order. In the first case, transactions are public, which is what we have for now for most blockchains. And based on the public information in transactions, attackers can decide to launch front-running attacks and also the famous MEV attacks. To hide transaction information, in the second case, users can commit their transactions and review later. However, commitments can only be reviewed by users themselves. This means attackers can selectively review their transactions and still launch front-running attacks. And to solve this transaction revealing problem, users can encode their transactions using time block puzzles. However, as we just mentioned, attackers can simply choose random information as time block puzzles and waste others' computational power. Therefore, this solution is only valid with a proof to validate time block puzzles. And let's examine how to validate time block puzzles before solving it. We will take the example of RSW time block puzzle, which is proposed by Rivest, Shamir, and Wagner in 1996. The first step is setting up an RSA keys. Based on the RSA keys to generate a time block puzzle for input S with time parameter t, the puzzle generator first sample a random number alpha and compute the puzzle z equals to s plus alpha to the power of 2 to the t, and simplify the computation using the trapdoor information. To solve the puzzle, the solver must compute t sequential squarings because it doesn't have the trapdoor information. The security of RSW time block puzzle relies on the hardness of factoring and sequential square assumption, and the modulus n usually needs to be larger than 2000 bits to be secure. To validate time block puzzles, let's first examine what we need to check. We need to check the puzzle Z encodes a solution S, where S is a hash of valid signed transaction with valid signatures with respect to the current state. This is a very complicated relation, and checking such a complicated relation can be solved by snark, for example with growth system. However, checking Z equals to S plus alpha to the power of 2 to the t within snark circuit is extremely slow. For example, with growth system, it takes around 72 million constraints and 5 minutes to prove, which is not practical for most scenarios. Let's see our result for solving this problem. First of all, we provide the definition of verifiable time lock puzzles, or VTLPs, with new properties of soundness, zero knowledge, and succinctness. And then we provide a very efficient construction for VTLPs based on snark offloading technique, which is 140 times faster for the prover time than directly checking time lock puzzles inside snark. And with this tool, we directly have applications for timed transactions, as we just discussed, and efficient verifiable time lock signatures. And in this case, we can reduce the verification time from 40 seconds to 1 millisecond. As a byproduct, we also provide a very efficient RSA signature offloading technique. And in this case, validating an RSA signature only takes 800 constraints, where 350 constraints for mimic hash with Go system. And this can be applied to batched signature verifications inside Snark, and our case is even faster than native field EDDSAs. We also provide a very efficient VTLP for RSA signatures and verifiable random functions without relying on Snark. And this can be applied to reliable distributed randomness generations. Due to time limitations, we provide a high-level idea of our technique. We simplify the original problem into checking alpha to the power of x mod n using Snark with public alpha and n and private x with the bit length of n around 2048. Our first observation is that we can first change x to its binary form and compute the powers of alpha mod n. Then checking alpha to the power of x mod n is the same as the following equation, which is a modular product of a set of integers. Our second observation is that checking the product of integers can be offloaded outside Snark with the help of proof of knowledge of double exponent in the hidden out group. And previous protocols have proof size verification linear with the security parameter or the bit length of the exponent. And our protocol has constant proof size and verification. Now let's see our experimental results. Our testing environment is a laptop with 8 cores and 16 GB of memory. Our Snark is Go system by GNARC. For verifiable time lock puzzles, our method is 140 times faster for the prover time than directly checking time lock puzzles inside Snark. And we can reduce the proving time from more than 300 seconds to only 2 seconds to finish the proof. For Snark signatures, our offloaded RSA signature is around 1.5 to 6 times faster than native field EDDSA signatures, which is also known as baby job. For 1000 signatures, we only need 1.3 million constraints versus 7 million constraints for EDDSA signatures. In conclusion, we provide the first definition of verifiable time lock puzzles, and we provide a very efficient construction for verifiable time lock puzzles based on Snark offloading technique, which is 140 times faster than directly checking time lock puzzles inside Snark. We also provide an efficient RSA signature offloading technique, which is faster than native field EDDSA signatures or baby job. We provide an efficient VTLP for RSA signatures and verifiable random functions without relying on Snark. And you can check our open source code and benchmarks in the following link and our online versions here. And this work is also supported by 3 academic research awards. Thanks for your listening.